Thank you, Marianna. Thanks to the organizers. As Marianna said, this is the last tutorial. I don't know about you, but my brain is already a bit fried. So I'm going to keep it, or try to keep it elementary, yeah. Please slow me down if I get fast. You know, at the board, time passes a bit differently. So yeah, ask questions. I'm not trying to do anything too complicated. I realize there's 4D here, so in the end, I don't know if 4D and easy is really compatible, but I'll try. Okay, so we already had one talk, yeah, by Sanjay on discrete integrable systems. This talk is a bit disjoint, but also the same. Sanjay, from my perspective, Sanjay did continuous integrability of discrete systems, yeah, because he looked at Hamiltonians and phase space, and that's a continuous space and so on. I really want to focus just on discrete integrability. And the plan is, I start very simple with in 1D, with 1D systems, then 2D, then 3D, and if we manage, then 4D. And I'll try to stick mostly to examples. Yeah? When I prepared this talk in the several waves, I deleted more and more of the formalization because it doesn't help that much, and with limited time, you can ask me about it otherwise. If you want to read up about it, there's this book by Popenko-Souris, which is called Discrete Differential Geometry, Integrable Structure. We're not going to do any discrete differential geometry today, because that would be like an extra tutorial. But we're going to take sort of the viewpoint that we take there in discrete differential geometry. But I think I'm not going to say one word about that in the whole talk. Okay, so far so fine. Yeah, otherwise, just, you can also just ask me, repeat the last sentence. It's fine. Okay, so following the plan. Oops. We start with 1D systems. And also following the plan, we start with an example. I'll fill in something after we're through with the example. Yeah. For now, it's a bit of a mystery. So what's the situation? Yeah, I'm going to look at. So I fix some function z2 to r2. Call this a drawing. Yeah, that's not any formal definition. So some essentially a straight edge drawing of some graph. Yeah, it doesn't have to be a planar drawing or anything. And it's almost correct. So I'm going to consider this drawing from the dual graph. So from the faces, and it could just be something like. Anything, yeah. I'm going to draw it like it's a planar thing, so it's easier, but it's not important. And now I want to find a second function. Yeah, I'm going to call it f. Which is now actually defined on Z2. And I want that f satisfies something. Essentially, I want a condition per edge. Yeah. So for every edge, let's say consisting of two vertices, VV prime. I want that FV is the reflection of FV prime about the line drawn by G, by our drawing. So, yeah. What does that mean? Or let's look at this. So if I have one point of f, yeah. Let's just recall. So the violet stuff is G, yeah. I have one point of f. Then I want to reflect it about the line of G to get the next point. Yeah. So if this is FV, This would be f v prime. Yeah, does that make sense? Okay, any problems with that? I mean, could you see any problems that come up now? Someone is nodding, but you know, Cedric maybe?
Something with corners? Something when you land up in the corner?
This graph, I mean, I just drew a small picture, but it's essentially infinite. If that's what you meant.
Consistency. Right.
Consistency, oh, that's a good word. Yeah, I like that word. Okay, so what does Misha mean? I have to go on, right? So this would be the next line, so I reflect about this. Then there's an edge here, I reflect about this. And now, to get back, I need to reflect about this, and that's supposed to be FV, but it really is not, yeah? So what to do? Any ideas? I heard? Yeah, we could change G, yeah? Maybe this is not a good G for this problem. So let's analyze. Now I'm going to explain. So let's analyze a bit how we can understand this. So we went around here. So let's look at this. Right, I start with a point here. I reflect it again. And this is a good point to take a break, because we can observe that, yeah, since I reflected about this line, these two distances are the same, and then therefore also these two distances are the same. And really, what I'm doing is, so these points are in a circle. I'm notoriously bad at drawing circles, so just imagine this is a circle. And really, I start here, I rotate around, yeah, not by some arbitrary angle, but really this is the full angle, and you see that like this angle between this perpendicular line and the line of G and this radius is half this angle, yeah? And similarly, on the other side, this angle is half this angle, and I don't know, maybe call this alpha and this beta. So in total, after two reflections, I have a rotation by 2 alpha plus beta. Yeah? So, but to get around the whole thing, I need to do this twice, yeah? Because sorry, I went slightly wrong. This is true what I said, but not what I wanted to say. Actually, I wanted to look at this angle here, called this alpha. Yeah, and the blue angle is twice this angle for the same reason I just said. Yeah. So it's just a rotation by 2 alpha. But then, if I have, right, so here would be alpha, but then if I do the other two reflections, I get a second rotation. So in total, I have this rotation by 2 alpha plus 2 beta. So any guesses now, right? We want to find out when this construction is consistent. So when in the end, this point is again this point. Can we translate this into a condition for alpha and beta? Right, we want to get the same point. It's a rotation by angle 2 alpha plus beta. What maybe has this angle to satisfy? So the angle should be 2 pi. Yeah. Could be any multiple, essentially, of 2 pi. which really means alpha plus beta is in pi set. Yeah? Okay, so we have some condition that we need to restrict to G. Now maybe I'm going to solve this. Okay, you either know or don't. So in this community here, this would be called a T embedding. Or at least it's a constraint that T embeddings satisfy. Yeah, in my community, we would call this a conical net. Yeah, meaning G is a T embedding or a conical net. Yeah. Okay, so now we have a condition. Now let's look at the problem again. Oops. Inefficient way to draw this, but we're looking for f. Yeah, we're looking for f. We're now assuming that G satisfies this angle condition. One point I can choose however I want. Yeah, this is an initial data. Yeah. Then the next point is determined, and this one is determined, this one, and so on. And here, in general, I have this consistency condition. Yeah, if you choose G correctly, then it's fine. Yeah, and then of course, you can do it everywhere. Yeah. So let me put that in a box because that's sort of the observation behind the standard notations. So we have 1D initial data. That's this point. We have, oh, sorry, that's wrong, of course. 0D initial data, yeah? We have 1D propagation because I propagate along edges my data, yeah? With these reflections in this case. And we have 2D consistency. Because I have to check around quads. Yeah. And so this is convention, but system is called a 1D system because it's 1D propagation. Yeah. And also now I can add, so there's not just one sense of discrete integrability. Yeah. So it's in the sense of consistency. Yeah, there's also sometimes called multi-dimensional consistency. Because once this works, you could also extend the solution to Z3 and so on. That doesn't make any difference. And Zn. Because you still only have to check around quads. Okay, questions so far? Okay. If you still remember a question, I can also ask later on. So what did I want to say? Right, so this example I want to formalize a bit at least, so that at least once we have a bit of a formalization. So that would be, for this setup there is specific naming conventions. Essentially for each dimension there are different naming conventions, even though it's always the same thing. So actually, we're looking at a group G, and with an action on a set S. I think it's sort of clear. Maybe, oh no, maybe not yet. But the set here in this example would have been R2, yeah, and the action would have. So the group would be O2, yeah, because we're reflecting. Okay, so let's do a definition in 3 points, I think. Yeah. A discrete connection is essentially a map from the oriented edges. I mean, it is a map from the oriented edges to our group. Yeah, such that for all edges, sigma just meaning if I go in front, then it's the inverse of if I go backwards. Yeah. And of course, since we have here reflections, and reflections are involutions, in that case, it's very trivial that that is satisfied. Okay. But then we had this consistency thing. So we call sigma flat. Yeah, so in general, not conventional would be what we could call this consistent, but in this special case, it's called flat. If and only if we look at these quads, if essentially around the quad, this is the identity. Yeah, I think that's clear. And if it is flat, then we also have these things called orbits. So always got to denote this by F, that now are actually defined on the vertices to the set such that we essentially have this relation that we just had here. So that neighboring FVs are related by this group action. And then we call F an orbit. Okay, why did I tell you all of this? It's a good introduction. 1D systems are good to start with. They're sort of everywhere. Yeah, it's a tool you use many areas of math. But it's not really very interesting from an integrability point of view. Yeah, there's not much more to say about them than I just told you. Of course, you can go crazy and look at orbits if it's not flat, and branched covers and whatnot, but that's not what we want to do today. Just to repeat, in the general wording stuff, this would be called a 1D system. If it's flat, it's called a consistent or integrable. One D system. And F is called a solution. Now you have some system. If you can propagate it, then it's consistent or integrable, and then the actual thing that you are propagating is the solution. Oh yeah, we had another example, at least one more example in the tutorials. Anyone has an idea?
Is this like flat connection have to do with that T embedding somehow? Like what's the connection between these two?
So it's just, in general, I could, as we start with general G, then I have a connection, but it's not flat. So it's just the case, those drawings that will yield a flat connection are just exactly the T embeddings. Or exactly the T embeddings one usually has some sort of embedding constraint additionally that we don't need, but yeah.
So like is it like what's the rotation matrix across an edge? Is it possible to write that down?
Yes, of course. If you work in coordinates, then I mean, I don't know the formula by heart, but you can introduce standard scalar product and then you reflect about the edge and then, yeah. So it's not I mean, O2 is maybe a bit too big because we only have, no, it's not too big. We have only reflections, yeah. We only use reflections for the group, but of course, as a group, reflections generate all of O2. Does that make? You still have a question, I think.
Yeah, like what, like what's the what's the relation between the reflection in O2 and that reflection somehow? Like, is it like, can you characterize?
I mean, let me check. So sigma is the elements of sigma are these reflections, yeah? And a reflection in the plane about a line is just defined to be, I mean, that's what O2 is about. Yeah. Reflections plus rotations, and you get rotations by composing reflections.
Yeah, because like the drawing closing up is not just the rotation being consistent, it's also like, it's like some Poincaré group, I guess, right? I mean, is the same thing, or is it like something?
In this case, we started with reflections coming from this graph, so it's like special elements in O2, because these lines intersect in points. I don't want to go too much into it. In the end, it has to be like this. You cannot have other reflections that do not come from lines that do not intersect. And then the connection will never be flat. But I don't want to go too much into that. Okay. So that finishes 1D, I think. Let's maybe go to no, I asked this question, other example. The height function that we saw in the beginning, in Cedric's talk. Yeah? He had this rule, I don't remember exactly, but he looked at quads, and then this height was determined by this height, and so on. Yeah? That's also an example of a 1D system. It's even more boring than this, sorry Cedric, because it's a linear system. Yeah, I just add +1, and this direction was +1. I forgot the convention. Here it's maybe -1, +1, oops, -1, and so on, yeah? And of course, this closes up here because it's just addition, which is commutative anyway. Yeah.
It's the case when the group is Z.
I mean, if the group is Z and you assign the same elements to parallel edges, then it's trivial. Yeah? In general, if you assign the same elements to opposite edges, right? And I don't know, here it's A, and here it's also A, and B as elements in the group, then the consistency is just about AB equals BA. Yeah? So then it's really just about commutativity in groups. So this is a slight generalization of commutativity in the groups.
For the height function, it was A, B.
I mean, for the height functions, from my point of view, yeah, slightly geometric point of view, maybe, you every edge carries +1 with these orientations. Okay. 3 is 2D systems. So we follow the same ideas, but in 1 dimension higher. What does this mean? Again, start with an example. Sometimes called butterflies. Why? So again, I'm looking for a function where this standard notation that's used in this discrete integrability community, like labeling is F, and then have F1 is if I go one step in the first direction, F2 if I go a step in the second direction, and F1, 2 means a step in both directions. Yeah. So, but that's just a combinatorial picture. For the map, I want to have a new constraint. So I have point F. See that I get this right. All right, so I'm looking at some map again from Z2 to R2, and this has a new constraint. That is, per quad, there exists a line, a symmetry line, yeah, such that F12 is the reflection of F, about this line, and f2 is the reflection of f1 about this line. Because you always get this sort of shape, it's called a butterfly. Okay, and now I can think about this story. How does this work in this case? So clearly, or not clearly, if I know f1 and f2, so I know, oh, I forgot to label one, sorry. f1 and f2, as soon as I know f2 and f1, this line is determined because it's the perpendicular bisector, which then means f1, 2 has to be the reflection of f about this line, which really means I can consider these 3 points as initial data, and then I get f1, 2. Yeah? And if I know everything on the coordinate axis, then I get all the points in this case. Yeah? There's no consistency problem so far. So far we have 1D initial data. That's all the points along the coordinate axis. I have 2D propagation, because now I propagate in quads, something two-dimensional, which means now I want to have 3D consistency. What does that mean? Let's draw a picture. So it means I should not just look at f here, it means I should look at f in Z3. No? So maybe I know, oh, I don't know if does this help? Yeah, I can't do anything about it. So if I know these 3 points as initial data in a cube, then this point is determined because it's a quad. Here again, this point is determined because here is a quad. This point is also determined because here I have a quad. So far, so good. But now, right, there's also the front of the cube. And this point is determined because, well, I know these 3. Yeah. But on the other hand, I also know these 3 also determine this point. And I know these 3, which also determine this point. Yeah. So, I mean, in general, that's a problem because this point will not be well defined. And there's no reason to assume by these 3 rules, 3 applications of this rule should give the same point. And if they do, if they give the same point, then we call it 3D consistent. Okay, I'm not going to prove this. You can see this as an exercise. I have a sort of proof here, which is you can just try to draw this. Yeah. What does this mean? Here, this is now actually the map in R2. Yeah? So here I have F, F1, F2, and F3 as my initial data. Yeah, and then I start building all these butterflies. So I'm not going to go through this in total. Yeah? If you're interested in this, take pen and paper. Yeah. But for example, F1, F1 to F2, highlighted in orange. See it here, F1, F1 to F2. Yeah, and then you build or glue together all these butterflies, and you will see in the end here, it's just 1 point that you need to get all these 6 butterflies. Okay, in this case, I don't want to do the formalization, but I want to get you a bit closer to the standard formalization at least. Let me see. I mean, you can sort of imagine what the formalization is, right? You have some sort of propagation per quad and so on, and then it's called consistent if it works on a cube and so on. But the standard formalization works a bit differently, in this case using equations and so on instead of groups and sets. So I'm just going to show how to make this system into a system that uses equations. Yeah. So let's make some observations. I look at one of these butterflies. One thing we observe is that f minus f1, for example, is necessarily to the length f to f1 is the same as f2 to f1, just because it's this edge that is reflected about this line, yeah, and this gives the other edge, and therefore it has the same length because reflections preserve length. And the same would be true for the other edges. Yeah. So the other pair of edges. And we introduce a number or a variable for this. Yeah, in the literature, these are called edge labels. Why? If you look at the bigger part of the solution, right? So here you have lambda 1, and it's the same on this edge, yeah, this length. And then since it's here, the same as here, but here also the same as here. It's sort of a conserved quantity, if you want, along these edge strips. And there's also, so you can imagine there along this edge there's one, along this edge there's another one, and then there's one here, and so on. Now we're almost there. Now I'm just going to write down the claim. So for this, we identify R2 with C, yeah, the complex numbers. And the equation that we use is the following. That's sort of the claim. This system is determined by this equation. It's one thing one can already see, sort of, if I take the absolute value of this equation, right, then up here I get one term of this, and here also one term of this, which is exactly what I have on the right-hand side. So for the absolute value, it's already true. So we still need to look at the argument, yeah, but that is true. So I always mess this up, but I'm going to try anyway. Let's see if this side, the right side, is real. So the argument of the left-hand side should be 0. Okay, let's try. First, let's look at this one. So I have f minus f1, which is this edge, divided by f1 minus f12, which is this edge. So the argument of this should be this angle, yeah? Remains to check this one. So I have f12 minus f2, this edge, and f2 minus f. So I should look here. And, right. Now it's this angle, which of course has the opposite sign of this one. since I'm looking at the product, I look at the sum of the arguments, so this is really 0. So that's essentially the proof that this equation is true. Questions? Okay, and this is called a lattice equation. I mean, the lattice in this case is Z2, or then in higher dimension Zn. And it's called a lattice equation because we impose this equation on every unit square, yeah, on every face of the graph. Okay, and with this additional thing that we have these edge parameters, yeah. So we have an equation per quad here, for example, but we also have sort of 2 edge labels that determine how the equation exactly looks, which are these conserved quantities along the edge strips. And this is how, well, this is the best known formalization of these types of 2D systems. It's these quad equations with these lattice equations with these edge parameters. And there's a big community around this, and there's a huge amount of literature about this. Maybe the most interesting thing is the classification of these equations. There's a paper by Adler, Bobenko, and Zuris called the classification of quad systems, I think. Okay, it makes some assumptions that I'm not going to tell you. And under these assumptions, it can classify all these equations here. Essentially, it has one master equation that looks super complicated and involves elliptic functions and so on, but then has several special cases that are much nicer to look at. This one actually being almost the simplest of them. Yeah. And of course, and you can also generalize by, it's not actually necessary that these are real quantities, it can also be complex quantities, then the nice geometric picture is lost though. I should also say, some people call this butterfly system or the butterflies, but it's also known as polygon recutting, which was originally introduced by Adler, who back then actually showed that integrable system in the sense that Sanjay talked about. So he introduced Hamiltonians and so on. It's also known if you just look at initial data like this, sort of one line and one point, and then determine this point, and then this point, and then this point, then there's a paper by Tabashnikov that calls this the discrete bicycle transformation, because it's a discretization of sort of bicycle tracks. It's also very interesting. And I'm sure there's more literature that I don't know. Okay, questions? Because I think that's the end of, or almost the end of 2D systems. I think I want to continue with 3D. But let me just say, in the last talk, yeah, we had Young-Baxter equations and so on. Yeah, I didn't know that this was going to come. You know what? Okay, maybe a small picture. Because that's, in a sense, a 2D system. Yeah, I mean, I don't know for the specific equations that were used just now. But just in principle, yeah. I mean, I presented the lattice view, and I'll mostly stick to the lattice view. In 3D, I'll change a bit to what I call the combinatorial view. There's another way to check consistency that I like more, actually, but it's less classical. Yeah, we've seen we need to check consistency around the cube, but I could assign initial data a bit differently. Yeah? Before we took it here on the coordinate axis, but I could have it here. And then I can flip about the quad. Yeah? So this point is determined now. So then there would be the next strip of initial data, essentially. And then I can flip here. And then I can flip here. This were 3 flips already. Then I look at the front of the cube. Yeah, I'm here on the right-hand side, and now I can flip here, right? And then I can flip here, and now I'm back. And now I can ask if I still have the same points as those I started out with. Yeah, and if I want to be fancy, I look at sort of this idea. So I don't know, maybe this is F1. So I would have F1. And then my first flip was here, F1 to. So I could draw it like this. And then I get, what's this? This is F1. This is 3, so it would be F1, 3. Yeah? So then I have 1, 3 here. Okay, I'm not going to go through the whole thing, but maybe you can already guess. Space is tight, but if you go through, so I started here, I'm almost back. Now you see, okay, this came back. This came back. This came back. Yeah, so in the end, I'm back at my initial values. I'm going a bit quick now, but you see I have 1, 2, 3, 4, 5, 6 crossings, which is essentially exactly the 6 quads of the face. I think traditionally it's called Young-Baxter equation if the values are not living on the vertices, but on the edges. Yeah, so then for a classic Young-Baxter thing, you would have something here. And then from these two values, you get to these two values. Then you can ask the same question, is this consistent, and so on and so forth. And there's also a classification, but for, I think, birational, something very specific. Yeah. Okay, questions to that? Okay, then that's now really the end of 2D. Which brings us to 3D systems, which, from my point of view, is the most relevant for this workshop, because, well, I'll explain. Okay. And I'm hoping to get the dimers as everyone else does, but I don't know if I will make it. So there are lots is exaggerated, but then some nice geometric examples and so on, but I don't want to teach a geometry course here. So I stick to a simple formula thing for my first example, which is called the cube recurrence, which I was actually hoping would happen in Terrence's talk, but didn't. And it's defined as follows. Yeah, you can imagine we're going a dimension up. In our first, in 1D, we had something along edges, then 2D, something along quads, and now we will have equations on cubes. So let's draw a cube. Right, we've seen this labeling a bit. I'm just going to repeat it. And okay, I just write down an equation like this. So now my lattice equation that I want to look at, which means I enforce it in every cube. It's an 8-point equation because it involves 8 points. Sort of similar to the octahedron equation that Terrence showed. And I'm not actually going to do anything specific for this example. It's just to show you there is one. Now let's discuss what happens abstractly. Yeah. So, okay, what's the initial data here? Yeah, I have an 8-point equation. I think it's convincing that I can choose 7 points and then generically solve for the 8th point. For example, I could choose these 7 points, and then this equation tells me how the 8th point is supposed to look like. Yeah. Okay, so that's one cube. In a bigger picture, I'm not going to draw all the dots, but you can imagine I can prescribe everything on one coordinate plane and everything on a second coordinate plane and everything on a third coordinate plane, and then I can start looking at my first cube and sort of insert a new point here. Yeah, so first cube. And then, of course, there's more cubes. I can insert this point, and then I can do the same here, and so on and so forth, and can fill the whole space. Yeah. Okay, so let's draw our box. Now, what's our initial data? What should I write here? 2D. Propagation is then (3D) because I propagate in cubes. Okay, that means I need to check for the consistency. Yeah. Which is my warning in the beginning. Now we need to think in 4 dimensions, which feels maybe bad, but okay, I don't know. I feel maybe I can explain it. Yeah, I don't know if you will agree. We'll see. So what do I need to do? I need to look at the 4D cube, yeah, because before we remember in 1D systems here there was a 2, so I had to check consistency in 1 quad. In 2D I had to check along a 3D cube, and now I'll have to check along a 4D cube. So, how to draw a 4D cube? There's many ways. This is maybe not the most beautiful, but I feel the most practical way. I just draw 2 cubes, 2 standard 3D cubes. Yeah? And I don't know if this is the origin, and this is vertex 1 and 2, and let's stick to what I did, 1 and 2 and 3 and 1, 3, and so on. Then I just shift the whole cube in the 4th dimension. So then here there's a 4, here's a 3, 4, here's a 1, 3, 4, and so on. Yeah, so yeah. What do I have to check now? Yeah. I have initial data, essentially a copy of this other picture. And then this one is determined. Yeah. So what about the 4D thing? Well, I claim I can also choose this one, this one, this one, and this one. Yeah. It's the picture actually how the initial data was in the 2D case. Yeah. And now, if I look at this point, yeah, it's actually in a cube. Here, yeah, consisting of this face and this face. So this one is actually determined by the 8-point equation. And then symmetrically, this face and this face determine this point, and the 2 bottom faces determine the last point, yeah, or the second last point, because now this point is still left. This point though is in this cube, so that determines this point. But it's also in a cube by the 2 top faces, where I know all the points except this one, and for this one and this one. So now it's 4 times defined. Yeah. And you can check using, I don't know, your calculation skills or computer algebra or something, that actually this equation is well defined. It will give you exactly 1 point here, no matter how you calculate it. And that is called 4D consistency. Questions? Okay. So let's do some combinatorics view on this, because now we're almost getting to our workshop. What I do is I draw an octagon. And then I fill my octagon with quads. So I tile it with quads any way I want. Yeah. Some point on the boundary I declare to be my origin. Yeah. Then I consider the strip of edges as being edges in the first direction, so that's a 1. Then I consider the next strip of edges to be edges in the second direction, so now I have a shift in 1 and second direction, and then here is my next strip, and now 1 is left. And here I'm at 1, 2, 3, 4, and this way I can label all the vertices. So that was a step in 3 direction, then I'm at 1, 3 here. That's 1, 3, 4. This is 4, this is 3, 4, and this is 2, 3, 4. Okay. And I mean, there's no closed cube in this picture. Yeah. So I can choose all these points as initial data. No. And now what could I do now that I have this initial data?
The cube recurrence.
I can do the cube recurrence. Where can I do that?
Where you have a degree 3 vertex.
Where I have a degree 3 vertex. For example, here. Yeah? You see, sort of, if I just look at this, I see the, I don't know, some will see the front, some will see the back of a cube. Or I could do it here. Yeah? So there's 2 points. Let's just pick one and let's do it here. Yeah? So I still have an octagon. I'm not touching this, so it's like this. But now here I press the cube to the back, let's say. Let's see if I can do this. Yeah. So here this point is replaced. If I look just at the strands, maybe someone have seen this picture. Yeah, I had these 3 strands. Now I shift over the crossing of the strands. That's the same as doing the cube flip. Okay. Is there any similarity if I just look at the tiling between these 2 pictures? Like in a geometric sense. I see some people who maybe want to say something, but say again? I did the cube move, that's correct. But I'm looking for an additional answer. Say again?
The isotope is that? Do you mean their isotope? Is that?
They are what? Isotope?
Isotope, you just drag like the vertex like halves the strength, the horizontal strength.
It's also true. Okay, there's too many answers. But what I want to say is, let's look at this lozenge, if you want. It's very special somehow compared to the other ones because it only has 1 boundary vertex. And here there was also one of these that has only 1 boundary vertex, yeah. But they're not at the same position. So really, this one rotated to this one, which was 1, 2, 3 steps. Yeah, so I have a rotation by 3/8 of 2 pi. Yeah. So really, if I do this cube flip now, not here, but at the other possible point, I'll again rotate by 3/8. Is that the word? I hope. Which also means if in total I flip and flip and flip 8 times, I'll be at the original picture. And then, of course, I can ask, well, if I did this flips 8 times, will I have the same values? Yeah? And that's an analogous way of checking consistency. One that I think is a bit nicer. I mean, that's not a real rigid expression, but I prefer this one a bit. And there's a second reason why I prefer this. You can define your favorite statistical system on a graph like this. Yeah? For example, we've looked at the Ising model definitely. Like, oops. So the Ising model would be defined on the screen graph. Yeah. Now, no one has talked about it, so you'll just need to believe me. But there's a way in the Ising model to replace the 3 edge weights associated to these 3 edges by well, we'll need to do the cube flip. By inserting instead a triangle here. Sometimes called the star triangle move because this is sort of a star and this is a triangle. Or the y delta move because this is sort of a y and this is a delta. And if you do it 8 times on a graph, turn out the edge weights will be the same as in the beginning, which is not at all trivial. I mean, at least from I don't see why that is essentially except calculating it. If you're familiar with it, the whole idea of the star triangle move is to preserve the partition function that we've seen in the other talks. Preserve means as a polynomial, sort of, it's not supposed to change, except for the variables that, I mean, it's hard to explain, that's why I'm not doing it. But so the whole idea already in the Ising model is to have some preserved quantity in the background, which makes it a bit believable why if I go around this cycle of flips, I get to the same thing as in the beginning. Okay, in my end remarks, I'll talk a bit more about how this discrete integrable system, how that is a relation between this discrete integrable system and the statistical mechanics stuff. But I actually managed to get to dimers, sort of, I think. So I'll do that. Unless there are questions.
How did you, will you say again how you drew the green lines?
Oh, yeah.
Which way, which diagonal?
So since I have a quad graph, it's bipartite. So I can just pick half the vertices of one partition. And per quad, I just connect them. That's all. So not much magic here. And then this happens.
And that 8-fold periodicity with respect to the y delta mean, those are for generic edge weights or just for the special?
Generic. That's the point, yeah. If it were for special edge weights, then we would be back in 2D systems. Because then the special edge weights, I think the critical, I mean, various people call various things critical, but I think what Baxter did in the back in the day is essentially a 2D law for the edge weights. And then if you have a 2D system, then you can choose all of this as initial data and set some stuff is restricted, but it will still be consistent around the cube for the reasons we discussed in the beginning, that consistency is automatically multi-dimensional. But yeah, the Ising model really features 3D consistency, so you can start with any edge weights, and it still works. And same for spanning tree model.
Not a question, but like a comment. So the same stuff works for like topological quantum field theories, like this derived Vera model. You can think of it as like a 2D space, and then it's like a partition function in 3D, which is like propagation. And this 4D consistency is like the pentagon equation, where you can glue a 4D tetrahedron.
I'm going to get to the pentagon equation in a second. I don't know about QFT and so on. It's nice that it works, but Okay, we'll maybe discuss after the next example. Yeah? More questions? Okay, time. I'm just going to look at an example, yeah, not the full story in the case of dimers. And I'll go with the example that I think we saw first in Pasha's talk, yeah? Which was triangulations. So I look at the pentagon, surprise, and the triangulation of the pentagon. Yeah. Then Pasha talked about the cluster algebra and so on, and then Terence talked about how cluster algebras relate to dimers, which is essentially I draw this bipartite graph by gluing in this star into each triangle. Is that clear? The cluster variables would sit at the edges and give this would only be two internal edges, so only two non-frozen vertices in the quiver. But I stick now to the dimer model, I think. Okay, so we have the dimer model, and then Terence explained that we can do the spider move, yeah? Change the combinatorics a bit. So in this case, we would get, I choose one of these edges, flip it, I leave the other one unchanged, flip this edge. I get here. Oh, I forgot the title. Let's call it dimers. Okay, and we've seen this cycle maybe a bit in disguise in Pavel's talk. But again, you see this vertex is special, yeah, because all the interior edges point there. After the first flip, it's here. So now it was a rotation by 2/5 of 2 pi, which means in total I need 5 reflections to get there. Yeah. And then actually, Pavel showed in his talk, if I look at this equation, it happens due to cluster mutation. Terence talked, it was the octahedron recurrence. Let me write it down and I'll explain a bit more as we go. So the variable set and the faces, the boundary I label like this. I'll explain why, don't worry. And so that would be a choice of labeling. Yeah? So at the moment it's just a random labeling, I'll explain soon. And if I go here, 2, 4. So, okay, maybe the rule is I assigned each vertex a number. 1, 2, 3, 4, 5, and then each edge just gets the label of the 2 vertices. Yeah? But there's another reason I will explain in a second. But now I can write down the octahedron recurrence. Yeah? It's this one times this one plus this one times this one, supposed to equal before and after. And it's called the octahedron recurrence. Yeah, you can see it involves 6 quantities that are essentially, as in Terence's talk, form this octahedron. And in terms of Cluster variables, Pavel proved by calculation in his talk that if I go around this one, I get the same numbers. Yeah. And the same is true for the diamond model. If I start with a diamond model with edge weights and then do it like Terence did, then the result will be, well, at least gauge equivalent to what I started with, up to possibility scaling at vertices. So the diamond model also features this relation. And okay, but like how does this fit in our whole approach? Except that I have a cycle in a flip graph and I get the same thing. I need a different lattice. That's sort of why it's almost at the end of my talk. Instead of Zn, I need An. Yeah. A3 is called the octahedral lattice. And you had pictures in Terence's talk. But since this is also a 3D system, and since we need to check 4D consistency, that's unfortunately just understanding the A3 lattice is not enough. We need the A4 lattice, and it's even worse because An is defined as the subset of the n plus 1, where the coordinate sums are 0, or could be some other constant. Yeah? For example, here it's 2. So let me explain. Right, A3 would, in this case, would be defined as a sort of level set in Z4. We need to check 4D consistency, so A4, so the actual lattice would be Z5. One can do that, but I don't want to. Yeah, and explains why this is a bit harder. But this picture is still quite nice. Yeah, it's even shorter than the other one because you only need 5 ones, and still captures the fact that we have planar initial data. Yeah, and still 2-dimensional initial data. A 3D flip because we flip in this octahedron instead of a cube, and 4D consistency because if you glue this together, it's 4 simplex in the A4 lattice. Yeah. Okay. Don't think I want to say much more on this. Can think about, I see already questions. Let me check what I wanted to say. Yeah, okay. Questions?
Because usually, like this flip move on triangles, you can think of as like gluing a tetrahedron on top of.
Exactly.
This. Can you like is there a way to like visualize the tetrahedron in terms of that octahedron that you drew?
I don't know. It's also, I'm only telling you part of the story, so it's not, I mean, for the octahedron recurrence, it's sort of true that you only need to check this cycle. It's not true, though, that in A4, there's only this cycle. Yeah, in Z3 and Z2 and Z1, there was always only one type of cycles. Generally, for like AN systems, A3 systems, there's 4 types of cycles. I always think of them as gluing octahedra. Yeah. In this triangulation case, you're right. It's like in this type of cycle, you can visualize it as tetrahedra because, I mean, essentially the edge flip, yeah, means we glue this extra edge. And then you sort of see the tetrahedron here, and then we glue the next, and so on. But for the other flips, it's not true anymore. It's not gluing tetrahedra, it will always be gluing octahedra. Doesn't matter, though, for the octahedron recurrence, but you could have cases where you have fields not just at the vertices, but at the edges or the faces or something, and then suddenly the other cycles will matter. In fact, a bit in disguise, but there was, for a long time, it was a conjecture by Dylan Thurston that the flip cycle of these bipartite graphs, like the cycles in the graph, in the flip graph, are generated by only 4 types of cycles of lengths 5, 10, and 5. And it was proven, I think, maybe now 3 years ago by Belitsky and Wellman. So it was open for, I don't know, 15 years or something. So it's only recent that you can actually, instead of looking at this lattice stuff, that you can actually, it's enough to look at the combinatorial view. Other questions? Okay, then I'll make final remarks, final rambling maybe. So we've seen, okay, didn't do it in details, but somehow easy model spanning tree model has to do with the 3D systems. We had this question about critical weights, which is somehow 2D systems. We started with these T embeddings, which Mariana will talk about on Monday, which are also related to diamond model. Okay, so big picture finish a bit, yeah, but no details. I haven't made comments about the literature in the 3D case. Yeah. Oh, yeah, and then remind me that at the end I say something about 4D, please. So 3D remarks. For Z3 systems, the literature consists essentially of a collection of examples, but there's no classification or anything. So there it's called the BKP, which would be the name for the cube recurrence. So D is for discrete, B is for the B-type Lie algebras, KP is for Katomtsev, Petjashvili, so 2 people. DCKP, and there's also a Schwarz inversion. Oops. BKP. Probably there is something here, but no one knows exactly. This is called cube recurrence. This is sometimes called Kasheyev recurrence. This is sometimes called double cross ratio equation. So everything has at least 2 names. Most of the time it's more like 4 and 5 names, which doesn't make it easier. For this workshop, this is spanning trees. That describes the flips in spanning trees. This is the Ising model. This essentially is about harmonic embeddings. Or, that's not completely true, but in harmonic embeddings, the flip, I don't know if you will see it at some point, but is governed by this equation. This would probably be about S embeddings. Yeah, some nice type of graph where you have a drawing in the complex plane where each quad has an incircle. Yeah, introduced by Dima Chelkak to study the Ising model. And there you also have a flip, and the equation governing this, I think, would be that's what we're looking for, but that's not so clear. Yeah, so there's still research, lots of research questions. Okay, 1 minute. A3 is a bit nicer. There's also a classification. Essentially, there's 2 equations. Yeah, the other ones are limits. The octahedron recurrence just called DKP, sometimes DAKP, yeah, because again, Lie algebra. That's a Schwarzen, like projective version. This governs the diamond model. This governs the T embeddings. What else? I think that's largely it. Some people have also proven that you can get these examples as reductions of the DKP equation, but on A5, even worse, yeah. Some people means that this inclusion is Goncharov-Kenyon and this inclusion is Kenyon-Pimentel. So sort of unwittingly, yeah, combinatorialists have solved problems in discrete integrable systems. Sort of why I'm interested in it as well. Okay, yeah, and please ask me questions after the talk. I'm happy to discuss this. If you do combinatorics, you know, there's probably lots of questions that no one has tried with combinatoric skills in that community. And this will be quick for the systems and higher, because that's it. Nothing else is known. Yeah? Of course, you can formalize and define a 4D system, but no one has found one. For a long time, yeah, people are looking for that. And so much that people are starting to try to prove why they don't exist, but that's still all we know. Yeah? Okay, let me finish with, I think I did hit another drawing. We had T-graphs by Mariana. You can also look at flip cycles. I'll leave this as a puzzle for afterwards, and that's it.